And so, hello, welcome back, guys. We'll just pick up where we left off. We're talking about functions and how OpenFoam deals with it. So we have found out that this is the form of the equation that we have kappa Reynolds number over y plus equals to logarithm of logarithm of the natural log of e times y plus. All right. So how does that look like our equation here? It looks almost like this. So there's a u plus equals 1 over kappa non y plus plus c. Alright, so let's just do a quick check. U plus equals to ln y plus, this is 1 over kappa, plus c. Now, just some things, yeah. It's possible that this c be incorporated in here, and thus it becomes this big E thing here. Alright, this big E over here, and yeah, that's how it's done. The only thing we don't really know what this is about is this kappa Reynolds number. So let's take a look at the source code. Take a look at the source code. Source code is here. So source code says kappa Reynolds number. It's over here. Kappa Reynolds number equals to kappa times the Reynolds number. So kappa times the Reynolds number. So really kappa times the Reynolds number. So this kappa and this kappa are the von Karman coefficient. They're supposed to be the same. Then there'll be some Reynolds number there. What is this Reynolds number? We'll take a look shortly. Scalar Reynolds number. Oh yes. So this is kappa Reynolds number. The Reynolds number is just defined before that. It is a magnitude of u. All right. Times y over the nu of the wall. Okay, so this Reynolds number here equals to the u velocity times y over what is that? Nu of the wall. So this is the nu at the wall. So let's break it down first. What is nu at the wall? Okay, nu at the wall, just remember that at the wall, nu equals to, the apparent viscosity, nu apparent equals to nu plus nu t. At the wall, alright, nu t equals to 0. So at the wall, nu t equals to just the liquid viscosity. So that's part one of the mystery solved. Second thing, we have the u here, but we have like this extra little y over. Okay, so let's do kappa Reynolds number over y. Kappa Reynolds number over y, or kappa Reynolds number over y plus here. And let's do some quick math. So you have a kappa over y plus. Okay, Reynolds number is u y over nu. Okay, so immediately you can see one group coming out. It is the group y over y plus. So I'll just rearrange kappa over nu, y over y plus into the velocity u. Okay, u is the local velocity, of course. So y over y plus is here, and kappa over nu. Okay, and y over y plus. So what is y over y plus? If we take a look back at our equation here, y over y plus, okay, or y plus over y. Can you see here this equation? Y plus over y plus equals to, all right. So I'm going to use red. Y plus equals to y u star, which is the friction velocity, because u star is denoted u tau over here, u star over nu. Okay, so y over y plus is simply nu over u star. Okay, so I'll just write in this color, k over nu, y over y plus is just nu over u star, which is nu over the friction velocity, times u, times u. Okay, so for sure the viscosity cancels out, and u over u star is just u plus. Alright, so kappa u plus. So this whole thing on the left side is just kappa u plus. Alright, kappa u plus equals to ln e y plus. Okay, so that solves most of it. We are almost there. So u plus equals to 1 over kappa ln e y plus. Alright, so you take a look at this final form of the equation here, and we try and compare it to this. U plus equals to 1 over kappa ln y plus c. Alright, so we see there's some resemblance. Alright, there's some resemblance, and of course if we expand this out, we have 1 over, if we expand out, we take the e out, 1 over kappa ln y plus 1 over kappa ln e ln of e. Okay, 1 over kappa ln y plus 1 over kappa ln e. So what is the c over here? It's supposed to be equals to 1 over kappa ln e. Okay, c is at the value of 5.5. Supposedly, 1 over kappa is 1 over 0.41. And e is 9.8, if I'm not wrong. 9.8. Okay, so 1 over 0.41 times ln 9.8. So let's do a quick calculation. First, 1 divided by 0.41 times ln of 9.8. And take a look at that. It's 5.566. 5.566. 5.566. So you see, it's very, very close in terms of this constant. It's very, very close. Okay, so you just I'll just show you the results over here, written nicely, of course. So this is the first part saying, oh, I just copied down from the code, and this is where I say, okay, this Reynolds number and is defined as u times y over the velocity, viscosity of the wall, kappa Reynolds number, and this is my whole like writing everything down. So this is swapping, rearranging the equation, and I tell you what kappa Reynolds number is, and I tell you what the Reynolds number is as defined there. Then we convert the y over here into some y plus times nu over u star, and say viscosity of the wall, apparent viscosity of the wall equals just the liquid kinematic viscosity. Then we do some rearranging, and then we find that, oh, kappa Re equals to this nice thing here, and we just substitute in kappa Re back here into this. Yeah, we get rid of the ones at both sides, and then we get this. We substitute kappa Re as this thing I'm highlighting here, and just copy and paste here, and you'll see that immediately we can see that the y plus cancels out with yp. Well, yp is y plus. It's just called yp in the code, and u over u star, or u over the friction velocity, becomes u plus. So u plus becomes 1 over kappa ln e into y plus. So we have this. So just note this, just saying this is an iterative formula. It is not time step based, and here we have the E carrying a value of 9.8. So we wanted to compare this to the original equation here. Then we'll have this, yeah, I have this thing over here. Yeah. So I was trying to combine this C, I did it the reverse way. I combined this C into this E over here, so that this whole factor here, I can put it into the logarithm here. And then this is supposed to be my E value. We see that it's also pretty close the other way around. However, of course, the error is slightly bigger because we're talking about exponentials here, of course. So the absolute error will be a little bit big. But if we check, if we check using this method, you can see that the C value is pretty much very close. So compare with E equals 9.8, this exponential being 9.535 is close enough. Okay, so this is our equation for smooth walls. Okay, so that's it for the smooth walls. For the rough walls, we can see this smooth wall function being used in a similar way. Okay, alright, so this is the smooth wall function being put here. We have a constant scalar, magnitude of u being such, and then we define, OpenFoam defines some Reynolds number, and it multiplies it into kappa. Then again, we have the y plus and the inverse of y plus for, you want to test the residual errors. Okay, but there's something a little extra here. It says here dks plus dy plus. Okay, so this is the additional thing here, and then we have this little roughness factor here. So we can talk about that in the next video. I'm going to talk more about this. Then we'll see how OpenFoam kind of deals with this little thing over here, the roughness. Okay, so we can talk about it in the next video. So thanks for watching. I'll see you guys again. Bye bye.